Yeah, we are live. Do we? What? So we are just scrolling links, right?
Mayor had a topic suggestion of robots learning from each other. And yeah,
Let me explain why.
You mean distillation?
Exactly. Exactly.
good connecting dots. I hadn't thought of that.
No, I mean, we've talked about bots selling skills to each other, but now we see trillions of dollars happening because of distillation. So, it kind of wakes you up. And the truth is that I don't have a good angle on how much work it is to train a robot. How difficult is it for a robot to learn a new skill? But I'm guessing that using a combination of distillation and other techniques that DeepSeek was using, even relatively small amount of CPU that a robot has might be enough in order to learn a skill.
So I'm trying to see how the analogy would work directly, because in the ML version of distillation, you have like an existing large model that has been trained from the ground up. And then its input output behavior, I think it uses something called soft tagging. So soft tagging is kind of like almost creating a rough version of its own behavior. And that soft tagging is what provides the learning feedback for the smaller model that's trying to learn. In robotics, though, I'm wondering if you try to maybe one way it could work is you train a simulated robot in a simulator with a lot of synthetic data. So even though it's a simpler robot than the real world robot, it's cheaper and easier to train, and it's sort of like automatically in a soft tag state. Since it's like ignoring a lot of detail, you can think of it as giving approximate simulations. Maybe that's one way to do it. But yeah, I'm trying to see how the analogy would actually work here.
But you're talking about how to do it. I'm first talking about what you're doing. So let's say I have a humanoid robot which has been trained to work in my kitchen. And I think another humanoid robot may be identical, maybe not. And I want to transfer that knowledge. And let's assume that both robots are willing. Okay, there's no faking here. So the robot that works in the kitchen would choose the equivalent of a set of prompt responses to show the other robot. And the other robot needs to learn those. And once it learns those, it already is halfway towards learning the skill of working in my kitchen. Okay, so that's the first step is, what does it look like? Afterwards, we ask how much power do you need? But that's a different question. Question number 2.
So I just Googled the first phrase that came to mind, robots learning from each other, and I found this phrase called imitation learning. So do you know anything about it? I think I've heard the phrase, but I never looked up, and it does seem to have some of the right buzzwords, like inverse reinforcement learning sounds promising, behavior cloning. So here's a video. Can I play it?
Here at TRI, we believe robots should amplify people at home and at work. To achieve this, we conduct cutting-edge research to make robots more flexible, robust, and general purpose. We've had a bit of a breakthrough. Today, TRI is announcing a new method to teach robots dexterous skills quickly and easily. Our approach is built on a powerful generative AI technique called diffusion policy. This allows us to teach robots much faster and with significantly fewer demonstrations. The approach holds great promise for creating what we call large behavior models. Like large language models have revolutionized chatbots, these behavior models will allow robots to perform useful work in ways never possible before.
Up until now, the majority of robotic manipulation work has focused on pick-and-place style tasks, where a robot is limited to relatively simple sets of objects it's rearranging. Our new approach goes significantly beyond that and lets us explore much closer to the limits of the hardware. TRI's robots are now capable of using tools, pouring liquids, and peeling vegetables. It's exciting to see them engaging with their environments in rich, multifaceted ways, and all achieved without changing any code or explicitly programming any new skills. Using this technique, we've taught over 60 diverse behaviors to our fleet of robots. The process starts with a teacher demonstrating a small set of skills through teleoperation. Then, our AI-based diffusion policy learns in the background over a matter of hours. It's common for us to teach a robot in the afternoon, let it learn overnight, and then come in the next morning to a working new behavior. To make this level of dexterity possible, every part of the robot platform must be solid, from the hardware all the way up through the entire software stack. One key enabler is providing human teachers with a sense of touch through a haptic teleop device. Also, just like people, we found that robots learn better when they have a sense of touch. And a perfect example of this is the task of flipping a pancake, where the robot has to make contact with a surface it can't see.
So I'm pausing it. Yeah, I don't know if you want to like see the whole thing, but yeah, this is like robots learning from other humans, which I guess is a one limit case, humans as like the original robots.
But you realize that the difference is that the human can only show what the human knows, and the robot can choose which atoms or behaviors are most effective.
Yeah.
Okay, I mean, humans don't know how to do it yet. Maybe tomorrow they will. But yeah, I mean, this is exactly the kind of thing, except we're not learning from humans, we're learning from robots. And then the next question is, how do I learn if the robots are not the same? And how do I learn a higher level behavior like planning? Planning isn't just I watch what you're doing and I do the same.
I
I get the sense from this video that the robots were learning from watching a human do it, but like understanding what it feels like to be remote controlled to do the thing.
I think from the phrases they used, teleoperation and diffusion learning or whatever, that sounds like an update of the methods they were using 20 years ago to like just record human pilot actions and like encode it as an automaton or something. This sounds like they use that as like a bootstrapping method. And I read something similar about DeepSeek, that was how their R1 model worked. The reinforcement learning there is bootstrapped by like examples of human chain of thought, and then you use that to like flesh it out, and then you get like more generalized chain of thought. But R0 is different. That one is not using human chain of thought as the yogurt starter thing.
Mm-hmm.
So there's like two strategies here. So this is, I guess, the more human starting one. I was also thinking of what you just said, Mayor. Like, if you want to like learn across different robots and higher level behaviors like planning, that reminded me of an example I read about some monkeys in Japan, actually, which is one of the first recorded instances of behaviors being learned by imitation that are completely artificial. So one monkey learned to wash the fruit it found just to remove the dirt and eat it more clean. And then all the other monkeys kind of like learned it, but that's kind of not learning individual muscle movements or behaviors, right? That's more like, oh, I see the end goal here and roughly how it's done, and I can kind of like just see the point of it and then figure out the details myself. So that's more like
Can you just say what you just said again? I see the point of it.
Yeah, so it's a teleological thing rather than behavior imitation. It's like, I see that this is a valuable goal, so it's like mimetic learning, I guess. I'll see if I can find that link. But yeah, this is like not behavior learning. It's learning that a particular goal is interesting and valuable, and you have to learn it because you didn't happen to think of it. Like the other monkey didn't happen to think that washing the fruit is a good idea.
So what you're really saying is one way in which robots are different from LLMs. The LLM just wants to learn to be an LLM, while a robot, even if it doesn't know why it wants a behavior, it has a specific intention to do that behavior. some sort of feedback loop that a robot can have that a LLM doesn't. And you also had it in the video where they said you teach it and then it learns overnight. So we can imagine overnight it's running simulation in its head and fine-tuning its behavior. You unmute.
Yeah, I think you're right. With an LLM, there's no natural way to complete the reality feedback loop and connect it to very basic cost functions like survival. You kind of have to be like in DeepSeek. What I read is, yeah, it just has to be like artificially rewarded for things like coherent abstractions on the way to responding to a prompt. But that's it's living in a equivalent of like a sealed off box, and you're having to shape artificial reward functions for it. Whereas in this 100th monkey effect, so parent, I don't know why it's called that, but yeah, you kind of have to yeah, let's actually just quickly read this. Yeah, one young monkey called Emo was washing sand off the potato, whatever. So it was either a very clever inventor monkey or just an accident. But 1952, 1958, collective consciousness. Oh yeah, so there's some sort of like social cascade phenomenon, blah blah blah. Yeah, so this, I don't know how real this effect is, but
Well, they say it was debunked.
it is an old study, so I don't know what the latest is.
Yeah, the second paragraph. It
Yeah, I
was
know. I saw
later
that.
debunked.
Yeah,
100th monkey phenomenon.
yeah. That's probably videos or something. Oh, here's a 100th monkey revisited kind of thing.
Yeah.
1985. So this is also about 40 years old.
Yeah.
The Japanese one. Okay, I don't feel like diving into this bunny trail now. I just wanted to reference it as like one framing of what we're talking about. So,
on Wikipedia.
does it add any more color to this?
I think there are other, not just monkeys. There's other animals that use tools and spread it in their social networks, like dolphins. Dolphins can use tools. They'll use like shells and sponges. I think they had some studies where like the mother was teaching it to their children, or I think there's also been some researchers who have interacted with dolphins, like in the military, trying to get dolphin help for their missions or something. But I think also just in the wild, they use tools, and people have studied how they spread their knowledge about that.
So they have to learn both things. They have to learn kind of that the goal is interesting and worth doing, and then they have to learn to use the tool itself, the behavior, right? In some cases, one is trivial, the other is non-obvious, and in other cases, like vice versa, right? Like potato washing doesn't seem like extreme for like extreme new behavior learning for a monkey. It already knows how to manipulate lots of objects, but like seeing that behavior and seeing the point of it seems like the more difficult part. Whereas like, a crow using a twig to poke out an insect, that feels like, all right, they kind of have to like get the causal reasoning of stick moves insect kind of thing.
Well, I have a book on cognitive behavior in animals, and what they say is that monkeys imitate on a regular basis. Okay, so, but on the other hand, I quoted from Wikipedia, and they say that there were only ever 59 monkeys. So there's no 100 monkeys. But let's assume for a second that these monkeys are little kids, okay? It doesn't have to actually be monkeys. The point is, you see one kid doing something, and then the other kids copy them. There's a need for motivation, and there's a need to learn the activity. And in robots, if you know what the goal is, and the goal can often be described physically, or at least let's call it as a way of affecting the world, you can close the loop once you have the intention. So yeah, I think that's very important. So maybe the monkey doesn't know why it's washing the sweet potato, but it knows that it wants a sweet potato to be clean.
Yeah.
It
So I
got
think,
that information. What does the end state look like?
and I think there's a computational angle there, because otherwise it would be intractable. Like all the monkeys all the time are doing like, hundreds of random behaviors. And if you just simply brute force try to imitate everything and find the 1 in a million behavior that's actually valuable, that's not going to scale. So there's some kind of like pre-processing going on and saying, hey, something, I'm connecting the dots, and washing potatoes is actually worth trying, whereas, I don't know, randomly banging tree is not valuable, right? So there's something going on that resembles reasoning backwards from a goal, and there's something going on that resembles reasoning forward from a state. So the classic AI planning forwards and backward regression versus state space search, both are inefficient unless you kind of have an idea why or how you're doing it.
They are inefficient, but they can find state situations that other more precise algorithms cannot, right? It's in reinforcement learning, there is this another dimension to the one you've just said, Venkat, is exploration versus
Exploitation.
right?
Yeah. So the AlphaGo Zero and DeepSeek R0 both are examples of that, right? In a computer, doing a lot of completely random experiments is extremely cheap, right? So the reason AlphaGo Zero worked is it could do the random strategy of like just try random playing strategies against each other, and there's enough brute computing power that you'll come up with completely weird playing strategies that normal humans wouldn't. But I think the more so this might be another difference with robotics. The more you're like in the physical world, the more each experiment actually costs a non-trivial amount of like energy or risk or something like that. Whereas, so it's actually, maybe this is an important unit, the cost of a trial of learning. So trying a new move in a game of Go is fundamentally very cheap. Trying like real action with a food you're eating, it's potentially dangerous, right? Take counterfactual. If the original monkey had, for some weird reason, decided to like roll its fruit in, I don't know, a toxic muddy swamp, and it ate it and died 3 days later, the loop is too long. Other monkeys would not have like connected the dots that eating poisoned swamp mud is what killed that monkey, but they might have tried it, right? So that's what I mean by the trial has higher cost, expected cost.
I want to point something out about the difference between AlphaZero, R0, and robots. And it has to do with volume. When I have R0 and I want it to be a ChatGPT, I want it to learn everything the ChatGPT knows. But what you just said earlier about monkeys is lots of random behaviors. I'm not going to copy all of them. That's part of the point. Part of the point is that you're not copying everything that the other monkey knows. Okay, so my robot that comes and watches a kitchen robot won't want to learn everything from it. It will just want to learn how to peel a potato. Okay, so this focus on what it is that we're transferring, from one robot to the other makes the problem both easier and more difficult. It makes it more difficult because you have to define what it is you're learning, and it makes it easier because your target goal, instead of being as good a chatbot as you can be, which is kind of vague, is peel potatoes.
I would push back against that. I think that's a fundamentally extremely limited, like ceiling limited strategy. If you're going to like anchor learning to like specific legible actions like peel potatoes. And the reason I'm thinking that is, have you guys read this book called The Inner Game of Tennis? So it's by one of the like famous tennis coaches, and his key insight was that when his students were like heavily fixated on like a legible named skill, like I want a better serve or I want like a better backhand, they would like overthink the conscious explicit logic of the, how do I put it, the uh, utilitarian reasoning behind the behavior. It's like you want to win the game of the tennis is the highest goal. You regress from that to you want to win the set, you want to win the match, you want to ultimately play a good stroke, and that's like, I want a backhand that goes cross court or whatever, right? And if you do that, you actually don't do the learning where it actually needs to happen, which is at like the very unconscious levels of like muscle memory and stuff. And his trick, and this is what he called the inner game of tennis, is every person learning has like a sort of like conscious critic learner that's like consciously analyzing everything it's doing, and it's usually getting in the way. And then there's this unconscious one, and his trick to coaching was, how do you turn off the supervisor part and like force the student to like focus on something else so that the muscle memory can pick up. So his thing was something like something arbitrary. I forget what the example he used, but something like, pay attention to your left thumb, which might be completely arbitrary and have no relation. But the point is, it'll like release your attention mechanism from the explicit goal you're trying, and you'll become more unconscious, and your stroke or serve will become better. So, and I think there's something very Zen about this philosophy. Like I read this book about long ago. It's called Zen and the Art of Archery. The same thing in Zen archery, they try to like force you to suspend your conscious learning mindset, and then somehow you internalize the unconscious stuff. So there's some angle there. So the point I'm making is, if you zoom out to how apprenticeship works, there's a reason apprenticeship is not the same as a list of recipes in a recipe book. It's more like you're an apprentice to a master, and the master may tell you a few things, like here's how you, I don't know, cut a piece of wood or some things, but 90% of the learning happens by unconsciously absorbing the, I don't know, quirks and idiosyncrasies of the master, right? Something like that. There's something there. I'm not quite sure where I'm going with this point.
I just want to give a story. I was listening to YouTube on learning how to play the piano. And when you learn how to play the piano, you have to learn the scales, which is kind of boring. So this guy gets advice from another guy, I don't remember the names, and he says, watch television. In other words, practice the scales while you're watching television or movies or something like that. And then you just build up the muscle memory while you're actually, your attention is captured by television. And the guy said, it was the most fun learning I ever had. For 2 days, I watched my favorite TV shows, and when I was done, I knew half the scales and could do them blindly.
When I've been playing piano scales, I think what actually keeps me wanting to play them is choosing something just a little bit beyond what I can actually do. So, like right now, that is playing a chromatic scale on 2 hands a third apart. And the fingerings for those are different in each hand. So, like, you really have to pay attention in order to get it right. And I've kind of been stumbling on that. But that's like more interesting to me than just playing a scale I've played many times before. I'm not as familiar with that one, but like if I just play, I don't know, C major or something, I get bored. Actually, that's a question. How much do robots get bored? Maybe that's an advantage over humans, not getting bored. I also wanted to say on the attention thing, AlphaFold, the machine learning for folding proteins, has it, like, you can't just brute force your way through folding proteins. That's why it's a hard problem. So it actually has like an attention model that they represent with linear algebra. And that's part of what makes it work.
if I were to use your words to answer Venkat, learning a task is an attentional mechanism because I'm focusing my attention on that one task, peeling potatoes, rather than just give me all you got. It's maybe not the best attention mechanism, but it is an attention mechanism.
I think you have to oscillate back and forth between different modes to like get full rounded learning. And this is, you see some effects of this in the AI stuff already, right? Like the mixture of experts architecture that most of the models are using now, the quote unquote experts, which are kind of like, smaller subsets of the model to which certain token generations get delegated, as asking ChatGPT about how all that works earlier today. And apparently it's, well, first of all, it's all emergent. It's not like somebody defines that this set of layers is for math and this set is for verbal. It's not like that. It emerges from the training itself. So what they do is initially the training inputs are kind of randomly assigned, and then sort of like in an emergent way, they start reinforcing, and eventually these like clusters of learning emerge, some of which make sense to humans. So there are things like, verbal generation or arithmetic processing or whatever, but other things are like less obvious, like, summarization might be an expert, and other things might be completely like opaque to humans. It's like this expert is doing something, and when it's deployed, it cleans up the input better, but we don't know what it does. So I think what you end up with in mixture of experts is what Marvin Minsky called the society of mind. So a million little agents, some of which do legible things, some of which don't do legible things. And in terms of like, I don't know, global versus task specific attention, getting bored versus staying focused and engaged, all that stuff, I'm reminded of how the brain works, right? So the brain has two basic attentional modes. One is called the default mode network. This is what's called mind wandering. And the other is called the task positive network. So they're in like different parts of the neocortex. So the default mode network is kind of what
Not exactly, right?
Huh?
There are different activations.
Yes.
Right.
So one is, I think, in the prefrontal cortex, and the other is just below or above it. I keep forgetting my neuroanatomy. But
the
it's
default mode, the default mode is across the brain. It's not just the region, right?
Default mode is kind of the colloquial term for it is mind wandering. So it's when you don't have any particular objective in mind. You're kind of just scanning the environment. Your mind is wandering. You're paying attention to whatever seems to be salient and popping. So this is kind of like, the brain scrolling through the world. So it's like the equivalent of scrolling, but for all of reality. And task positive is something like, all right, I've wandered enough, but here's a potato, I will wash it and eat it. That switches you into task positive mode, right? So, I think
you're not talking about anatomy because, like Eric said, it's a default mode network. And when
this is like
peeling
human
a potato,
is this is like, I would say the human is one way of embodying basically the exploration exploitation trade-off in neural hardware. And maybe LLMs do it differently, maybe robot behavior models do it differently, but I suspect if the computational substrate is rich enough, so somewhere in the billions of parameters or whatever, you will see the same distinction emerge. There will be modes for wandering, there'll be modes for focus, there will be behaviors that look like getting bored. So yeah, being bored will emerge, I think. Sufficiently rich substrate, robots will be capable of getting bored. It'll be a feature, not a bug.
Can you explain again why you see being bored? Sorry, please.
Also, I'd like to interrupt because in a few minutes, if there is interest, one of my friends has a Turing Pi, and he's okay. He's a DevOps engineer, okay. So working server side, but he would be interested if we have any question to join and to show it and answer questions. So he should be available in a few minutes if there is interest.
I vote for it. I want to get a pure Turing Pi as my second RPi computer after I start building my.
So I'll ask him, Maya, sorry for the interruption.
Yeah.
No.
Yeah,
important interruption.
We can finish this boring.
I wanted to add,
yeah.
Yeah, no. So Venkat, I don't understand the connection between default mode network and the process of learning. Could you explain it again?
So
Exploration,
there's probably some
exploitation.
evidence for this, but I would say that being bored, the affect of being bored and the subjective state of being bored is actually when the default mode
Mhm.
network activated in like a slightly off-tuned way. So you are in the default mode network mode maybe, but maybe you're feeling a little too energetic and it's like not focused enough for you. So you're like restless and you want to like latch onto something more focused and do it. So I would say being bored is somewhere in the range of a default mode network behavior. And if you, for example, if you relax a little more and say, hey, all right, I'm just going to relax and not get frustrated, then you might get into a meditative reverie and have some creative thoughts, that kind of thing. So that's the connection I was making. I think being bored is actually one of the macro states within the default mode network phase space.
Okay. So what you're saying is that's how you move from exploration, from exploitation to exploration. Okay, got it.
Yeah. And there's research on this. NVIDIA has
There is
research.
neuroscience, yes, and also studies of psychedelics shows that for creativity, but also for learning. Okay, you have more and more proofs, in neuroscience by tools like psychedelics to actually show that, which is really really interesting, actually. Yes. So sorry, just Liam just showed up. I'd like to introduce him to you. So Liam and I are working together here. So it's a robotics company, but we are working mainly on the DevOps side. Okay, so infrastructure for making robot software. Okay, and we are exploring different technologies. Okay, so it turns out that we got a Turing Pi very early. So I think it was early. Okay, but we only started recently, maybe last month. Liam started to. He the one who got it. Okay, so people were contending to get it, and he the one who got it. And so so for us, it's to use server side. Okay, but if there is any question, or I think Liam can also. I think you can show it. Okay, questions about how it is or whatever. Okay, I'm glad that to welcome Liam. And Liam, this is the group we talk about sometimes about rovers, YaRG, and AI and things like that.
Cool. Yeah. Thank you, Eric, and thank you for having me. Yeah, I help Eric's company out with DevOps stuff, and I managed to take the Turing Pi before anyone else did. It's without the case here. We didn't order a case, which in hindsight was a huge mistake. But yeah, so yeah, I can talk a bit about it, or if there's any questions, I can also just go to answering them immediately.
So we can't buy these? Is that what you're saying?
So I believe, so we got ours by pre-order, and I believe there's been some issues with I believe most of Turing Pi stuff is mostly based on pre-orders. I know when we considered buying one of them, we basically we put in a pre-order. There were no units, nothing available for purchase, and then we had to wait for
A few months.
yeah, a few months for the shipping date, and then it was delayed like half a year or something. So we ended up getting the Turing Pi like half a year after we were supposed to. If it's available now, then yeah, that's good. I think what's very interesting is I think one of the original reasons why we wanted the Turing Pi was because at the time we were experimenting with a lot of AI driven stuff, but by the time we got the Turing Pi, we'd actually kind of pivoted away from it, which I think is pretty funny. But yeah, I believe one of the some of my other colleagues are still planning on trying to experiment with doing robotic simulation on the Turing Pi because well, I mean, as you may know, ARM is kind of hot at the moment, and it's also great for embedded computing and robotics, and also because running in the cloud is a lot cheaper. So I think there's a huge agreement at our side that ARM is kind of a very interesting place to gain some more experience now.
What do you have on your Turing Pi? Do you have like all RPi modules or also a Jetson module?
Yeah, good question. So I have one Jetson. I believe it's a Jetson Orin. Yeah, it's the small Jetson Orin with a heatsink. Sadly, and you'll find people complain about this on the internet as well. The stock NVIDIA Jetson Orin fan cable is very short, and so it doesn't actually. It's not long enough for the Turing Pi board. But I haven't been able to. I haven't even flashed the Jetson yet. I haven't had time to do it. But I, based on what I've read, for non-ML workloads, like if you just want to get things up and running, it's fine with just the passive cooling. And then I am currently verifying the connector type, and I'm planning on just buying an extender cable or something. The rest of the chips are Turing RK1 compute modules, and these are very interesting because the fan cable still attached.
Please don't break it. We have only one.
Sorry. So the Turing RK1, it looks like this. It comes with a cooler. No, you have to buy the heatsink extra. But when it idles, the fan doesn't spin. Although now that I've installed the K3S on it for testing, the fan constantly spins. What's very interesting about the Turing RK1 is that the chip it uses, which is the Rockchip RK. Let me just get you the exact chip here. Yeah, it's the RK3588. It's a very famous and hot chip on the market at the moment. I believe it's the one of the most powerful ARM chips that consumers can just readily buy. And as a result, some of you might have heard there's this guy on YouTube who basically he made his own motherboard for the RK3588, and he built a whole laptop around this chip. But yeah, it's a very, very powerful chip. It's more powerful than the Raspberry Pi 5 chip. It has 8 cores, and I believe each core is also a bit faster than the Raspberry 5 core, although please don't quote me on that. But yeah, so I know other people as well who use the RK3588 chip in other use cases, and the reviews are all very positive. Like it's a very people are very happy with this chip, and for some applications, it seems it's kind of from my point of view at least, it seems that this chip is a serious contender to the Raspberry Pi. The only big downside here is that the Raspberry Pi has amazing Linux mainline support, while with the Rockchip series of chips, you'll have to use some kind of fork that has the necessary drivers, and that's not necessarily always a good thing. The Rockchip, the Turing RK1 compute module comes with Ubuntu firmware, but I believe the guy who maintained that firmware, the Ubuntu Rockchip firmware, which Turing Pi has forked, has quit because basically nobody paid him, and he burnt out because of expectations, which is a common thing we see in open source at the moment. But I believe the Linux fork that this Ubuntu fork is based on is still maintained and happy. But basically, these kind of Linux drivers not being in mainline issues and things like that is it's apparently pretty common with these Chinese ARM chips that are pretty much. It's still kind of a startup Wild West over there, it seems. But but it's very promising, and so I think it's a very interesting compute platform, especially if you want experience with cluster computing on ARM. Yeah.
Just one extra, because the board also has an NPU, the neural processing unit.
Yes.
So aside the main CPU, which Liam just talked about, and this NPU, according to the specs, it's 6 stops. Okay. So remember last week we talked about the I forgot the name, the Ion 8, okay, the Israeli company, where they are between 13 and 26 stops. Okay, so just to compare, because the chip is the one for the AI plus Pi hat we talked about last week. Okay, so just to compare, so here is only 6 stops. Okay, according to the specs. So it would be at least half the power. Okay, the thing that it's all integrated. Okay, so in terms of space. Okay. In terms also of, we don't have a moving part, basically. It's soldered on the board. Just to link to the discussion of last week.
Yeah, I mean, it's worth noting the Jetson Orin board that we also have. According to the specs, this is the 16 gigabyte model, which advertises up to 100 sparse int 8 tops, or up to 50 dense int 8 tops. So, I mean, the Jetson Oryx is still basically an order of magnitude faster if the rock chip only had, what did you say, 8 tops? Yeah, 6 tops.
6 tops.
So yeah.
And the Halo 8 was 13 or 26, right? The Halo 8 for the AI RPI hat, I think so. That's what it was. What's the power consumption on these Jetson and this other module, the rock chip one? And how does that compare to the RPI 4? I think the RPI 4 is what goes on the Turing Pi, right?
Yeah, a good question. Yeah, I believe I don't think we even have an RPi 5 compute module yet.
No, we don't.
Or was it recently announced? Oh, it has been announced and it does exist now.
Okay.
Yeah, but the compute module 5 has a different board layout, so it won't fit in. I don't know what the expected power consumption is. I kind of assume it's same ballpark, but I think what I want to show is this is the power brick for the Turing Pi cluster board. So I mean, of course, the Turing Pi is a beast, and it can handle a lot of peripherals. Like on the bottom, you have space for NVMe drives. There's some SATA. There's a SATA controller. There is. I mean, one thing that makes this really good for cluster computing is the fact that there's an internal Ethernet switch, which is 1 gigabit per second, and it has 2 cables out, so you can have redundancy there. But yeah, so there's a lot of things here, so it makes sense that even outside the modules itself, it consumes a lot of power. But this power supply is rated for
20 amps, I would guess.
Yeah, 12 volts, 12 amps.
12
amps. Wow.
Yeah.
That's a lot.
So 150 watts.
Yeah.
Which is a lot. But yeah, I don't know about the rock chip power consumption.
150 watts is basically a normal rack scale server rack, right? So you get 175, 150, 300 of the typical cloud data center power slots, I think.
Right.
Yeah.
Okay. So
I mean, a gaming laptop often survives on 120 or 150. Like that's kind of yeah. So yeah, I would get more data on the individual chips. But one opinion I've seen a lot about these single board computers is that they could make sense in a very severely resource constrained environment. But as you said, like a normal rack spends around 120, 150 watts. I know my servers spend around that at least. And for the price of a decently kitted Raspberry Pi 5 with like an NVMe hat and maybe a PoE injector or whatever, you're almost approaching the price of, like, at least for a hobby from a hobby point of view, you can probably buy used Intel NUCs that are cheaper or the same price with more performance. So I'm still cautious about like real world applications of these outside like severely power constrained environments.
This is basically a good toy experimental test bed for cluster computing.
Yes.
If you want to do that. So
Is communication between the modules restricted to the 1 gigabit switch? Is it over Ethernet?
Yeah, I believe so. I can double check that for you. TrinkPy 2 Intron specs. If you, I'll just send a link to the docs here.
Just on the earlier question, to compare the CM4, CM5 to the TuringPy RK1, so okay, is that I remember reading that the RK1 was more economical, okay, in terms of power. So sorry, I will try to find a link, but I remember reading that at some point.
Can you?
Sorry, what were you saying?
No, I just wanted you to give a feeling for what applications might enjoy this kind of power.
It's hard to tell. I mean, the TuringPy guys are kind of advertising this as a test bed for like home labbing or learning. I mean, they spend a lot of time saying basically, oh yeah, use this to learn Kubernetes. Or you could do like a home server with like a and use the M2 SSDs on the bottom to have like a redundant fast storage or something. I think it makes most sense in a home or small company setting. And I think basically I know you guys talk about robotics and AI. And I mean, sure, like if you want some super redundant system where you have multiple processes of the robot spread over multiple nodes, then this might make sense as a test bed. But you still have issues like, the 1 gigabit internal switch, which, it's enough for most cases. But if you want to stream video or something like that, or, there's some limitations on like which board has access to what peripherals. I think, for example, the SATA ports only have access to the first node, things like that. So I feel like if you want to do anything with that generates a lot of data or that needs to pass a lot of data between the nodes, I fear that you will hit bottlenecks relatively quickly. But I mean, if you're in a case where you want to build something like that, then maybe it makes sense for you to design your own board instead. This can still be a good test bench for proving that something that your idea is feasible before you scale up. But yeah, I think it's best for testing, to be honest. And that's also what they advertise, basically.
Or hacking as well, right?
Yes, testing, hacking.
Because perhaps one of the appeal of the TuringPy on a robot, maybe to have different compute. So it's perhaps not having a Kubernetes cluster, for example, but why not? Okay. The point is to have several computes with different aspects of what a robot is. So at some point we had like a lower level motor control. So all on perhaps an MC is enough, okay? And higher level, and so perhaps machine learning and so on another board. Okay, so there are separate compute that are reserved for a specific kind of payload. Okay.
Yeah.
So that's how I think that's where there is some appeal to something like TuringPy in our discussions. And so, of course, we're thinking about making something production ready to sell next to iRobot, basically.
Yeah, it's kind of funny because it feels like a little data center rack in a little tiny footprint. But then it's also got stuff like the 40-pin GPIO and a SIM slot and all these other things that are more like Raspberry Pi hobbyist things. Like, Who is it for?
But it sounds like you can build a DeepSeek robot with it. In other words, you have all the GPIO to control the robot, but you have enough power to train on board. Maybe using the new algorithm.
I think you can do inference. I don't think this has enough power to do any level of meaningful training, at least from what I've seen. Maybe in the future, but
I don't need a full LLM that knows 50 languages and the entire whatever. Okay, we just want robotic movements. You know, it's a lot less, much smaller vocabulary.
possibly, yeah. I think the reason it interests me is the architecture we've been talking about with a little brain and a big brain. So for Liam's benefit, we've been talking about this speculative design called the Yakasor with a low power little brain, Arduino class that uses very little power but can do basic robot control, or an ESP32 with some connectivity. But big brain would be RPi class that can run full Linux and some heavier programming, maybe with like some AI acceleration and stuff. And also maybe run like a cell phone wireless modem for off-grid operation. But this makes me think that the little brain is probably always going to be a bottleneck. Like maybe there'll be a little redundancy. Maybe you have 2 Arduinos or ESP32s, but the big brain, it's kind of interesting to think what happens if you have like 4 brains, right? Like I think the Mars rover has 2 parallel brains, and they kind of do like it's both redundancy and voting when you're doing like decisions where you kind of need both to agree or something. And lots of people talk about architectures with tie breaking, like there'll be 2 independent computes and the third compute will break a tie in case one of them has like a mistake, right? So that sort of thing is possible. Yes. So 1 or 2 small brains, 1 or 2 big brains, and then I don't know. At this point, I'm just almost looking for an excuse to go down this bunny trail. It's fun. Running a little rack of servers on a robot seems like a fun idea to even try.
Yeah, I mean, if you're looking for fun, then I really think this is it. It's good fun.
No, I want to say again.
Some serious punch.
So the cost also is it's not extreme. Right? What the main board is what, $200?
Yeah, I think it's $200, and then it's what,
No,
$100 per board? No, per rock chip.
Well, 200 for each one of the 5 components. I mean, $279 for the board, and the rock chips are between 180 and 300. But for $1,000, you can have and then add another $300 for the robot, a walking cloud computer.
Yep.
So does it come with the software?
Walking cloud computer. I have to process
exactly.
that.
It's like clouds in the sky, except on the ground. Does it come with the software for virtual machines and all of that stuff?
Well, I mean, it's since it's Linux, you can basically do whatever as long as it works on ARM. So, for example, one thing does ARM. So you do have a lot of open source fans will know of something called Proxmox, which is basically like VMware but built on top of Linux. It doesn't officially support ARM, but what it basically does is it helps you orchestrate LXC containers, which is basically just Linux containers with no Docker stuff on top. And KVM virtual machines. KVM is a kernel feature of Linux. So basically, as long as the rock chip supports virtualization, you can pretty much just run normal Linux virtual machines on it if you want. But I think with the size of these and the power of the CPU, I don't know if virtual machines is really the way to go anyways, because of the operating system overhead. I would much rather prefer containers in a resource-constrained environment like this, I think.
But
And so there are very big differences between VMs and containers. Just it's conceptually it can be they resemble a lot, but there are a lot of differences. And containers are much more lightweight, by orders of magnitudes. Okay, it's something that Liam and I talk about more and more these days. That for robotics it looks like containers would help a lot. Okay, and so if people here have touched something called ROS. We talked about ROS. For me, this is something very important. Containers could help the user of systems like ROS, basically, because right now it forces you into many things that we can make disappear with containers.
Yeah, and if you've I don't know what you guys' background is, but if you have any experience with Linux recently, you may have noticed either Flatpak or the alternative to Flatpak.
Snap.
Snap. Yes, Snap. And I believe both of them are glorified containerization tools. Where the goal is basically, I mean, the whole idea with containerization is that we just ship all dependencies in a container, and then we don't have to care about the what the system has installed already. Snap and Flatpak are basically just different solutions for doing that. So I think the Linux ecosystem in general is also going in that direction. It seems we've kind of just given up on the whole, the keeping multiple versions of a dependency on the system and loading the right version of the dependency for the binary that's being started, things like that. It seems like, because of how cheap storage is, we've kind of just come to a conclusion that we're okay with spamming our disk with the same binary 1,000 times, as long as it means that we don't have to deal with dependency hell. So yeah.
Okay, so just to think about what we've talked about with robotics, we can have a robot walking along, and it sees a rock, and it says, "Oh, maybe I should make that rock into a tool." So it spins up in its container a simulation of robots, rocks, and tools, and runs it in the background. Okay, so having this kind of power for self-training on the go, I think could be very interesting. Because one of the things that can happen that's, I think, more difficult to do in the cloud is you can have leakage from the real world into your simulations. Okay, so the robot was trying to figure out how to use a rock. It's running a simulation, and then it discovers that one of its legs is half broken, so it can't make all these motions. It immediately feeds it back. Okay, so it's very tightly coupled learning and planning and simulating going on. $1,000 is a bit high, but this is, getting close to a different type of robot than what we're talking about. We've been talking about a robot that's stupid, a robot that is smart in that it can run more sophisticated algorithms, and a robot which can be connected to a cloud to get services from the cloud. But here we can have a robot which really is self-contained. So I'm just saying it. Imagine every move it makes, it can run 20 simulations to see what will happen. We couldn't really do that before in a walking robot.
Another thing that becomes possible with this much power is Anuraj has been trying to run Ethereum Lite client on robot class machine for a while. I don't think it worked easily, but I think with this much power, yeah, you could just devote an entire RPI to just running an Ethereum Lite client and put it on chain, basically. So that's
the Lite client concept is changing. So basically, previously you used to run a full node and then they used to serve, but right now they are working on something called Portal Network.
okay.
So it's basically a lightweight syncing mechanism, and the data is distributed. I don't understand it fully, but I just started reading about it.
Oh, okay. So does that make things easier or harder?
Yeah, it makes so the hardware requirements really go down. So I think you could basically, when the network is live, so it doesn't do all the things, I think. So it's like, and the data is kind of distributed among the nodes. So it's right now also in test phase. They're not deployed it yet.
Meyer, I was thinking back to your question near the beginning when you're talking about how can one robot learn from another robot when the robots are different. And I was kind of picturing in my head at the time, like, what if one of the robots is small and the other is big, and one has to teach the other how to move in your kitchen or something? They might have to do the same tasks in at least somewhat different ways. But I just, talking about the dependencies, I just thought of another way that robots could be different from each other. Maybe they just have different dependencies. I have to learn in that context.
What do you mean by dependencies?
Software dependencies, like in Linux. Like, I have definitely had experience using Linux where I updated my software and things stopped working because the dependencies changed. So they're like interrelated modules of software, and they rely on each other, which means like one piece of software is dependent on another piece of software, and everything's kind of modularized, which is kind of one of the things that makes Linux cool. Terrence, would you please be quiet? I'm talking on the video. He's very excited right now. But yeah, like I've definitely had like games that broke because the dependencies weren't updated, or they were updated and they broke the things that were working with the old version. Or I mean, Snap will protect you, and Flatpak will protect you from that somewhat, but not all the way. So you could just have robots relying on different packages of software, or even different versions of the same modules of software, and having to learn from each other. And like, I don't know, it just occurred to me that's a different way that robots could be different from each other.
We have been ignoring this issue of dependencies, either by looking at an individual robot, or what we've been doing is talking about some abstraction level like ROS or an LLM, which is a one unit, so you don't have any dependency issues inside. But you're right. Okay, I mean, even if you take an LLM and apply it to robots, it's already not one unit anymore. You already start getting subunits, and things will really be different. So basically what you're saying is the internal architecture is going to leak out into the ability to do certain activities.
Yes, I know. On Linux, something that breaks quite often is anything involving NVIDIA, by the way. Huh? So you often lose your GPU. So we talked about video games, graphics, and so simulations, machine learning. For me, sometimes I do an Ubuntu update, okay, because Ubuntu is the main operating system for NVIDIA. But I won't say main, but people who do machine learning, it's often the setting they have, okay? You just upgrade Ubuntu, and suddenly NVIDIA doesn't work anymore. When I say suddenly, okay, frequently, okay? It happened to me last week again, okay, so the dependency is definitely a big problem. What is interesting, though, is that machine learning, this component, is not part of operating systems today, okay? Because operating systems are very, very super well-oiled machines, right? So we don't want statistical stuff inside it. But Ellen mentioned Snap. Okay, Snap is a package manager, a software manager inside a system. Okay. So Snap and others, okay, apt, Yum, all those names, basically they implement, search algorithm that 30 years ago were AI, by the way, okay. But the thing that maybe there are some opportunities to go down there, okay, and perhaps to use machine learning and so on, perhaps including LLM, okay, to be able to, at runtime, solve these dependencies, okay. So that would be super interesting. But looking at the diversity of package managers and the fact that all these packages are developed across the world by many different people on different schedules, it sounds like super hard to guarantee that everything works all the time, basically, right?
There's also another very big issue with package managers, and that's the fact that package managers are really only as good as the system they're running on and the software that's using them. So, for example, you can have your whole system maintained by a package manager, but the second you compile some software yourself, and the packager doesn't know that that software exists and has that dependency, like you will have issues with like the version of the library that the software you compiled was compiled against being garbage collected because the package manager thought it could upgrade all the time. I used Arch Linux a lot, and I would see this issue with they expect you to build all the non-supported packages from source, and what will happen is if you don't rebuild often enough, you'll have issues where these packages that you have to build yourself will just stop working because they've kind of designed the system where the packages that are outside the officially supported list are just not cared about by the package manager.
This reminds me of what used to be called the frame problem in GoFi. The world only changes if the AI changes. That's the frame assumption, right? It's like nothing changes in the world unless I change it. So it sounds like package managers make a version of that assumption. So if the frame changes outside their control, you've broken the frame problem for them. So I was thinking in relation to the Turing Pi, you said something like, some slots, the slots are not the same and the SATA is on one slot and things like that. That suggests sort of an interesting interface between like the hardware versus software kind of like learning problem, right? If you have two identical hardware configurations with the same peripherals, and you know that a particular Docker container with like some robot control code is working on one, and that RPi breaks, and you have an identical RPi, you can just download the container on the other RPi and it'll still work.
Right.
But if you have some slight differences in like, one has a SATA drive, another has an NVMe drive, or one connects to the motors a different way, you're screwed, I think, right? So there's like learning at the outer similarity level. So big robot versus small robot, 3 legs versus 4 legs or whatever. And then the inner one, the configuration files are like similar for like half the ports, but the other half of the ports are different. So this sounds like, I don't know, an AI complete type problem. Like solving it would be solving everything.
Yeah, there's the problem of whether or not you can replace the same unit with a different one. But I think another similar problem, at least with the Turing Pi, that's worth considering is the fact that they advertise. I mean, the whole idea is that you get this redundant computer, right, where something can die and then you can replace it with something later. But when the peripherals are different from machine to machine, you lose that redundancy. So in practice, the second you use, basically for a robotics use, the second you use any peripheral, as long as you don't have an architecture where multiple nodes can talk to the components at once, you don't have any redundancy in practice.
Yeah.
And that makes a cluster technology actually pretty appealing. Okay.
Yeah.
But I think one of the really nice things here, if you don't need redundancy, but just care about, someone mentioned earlier that you can spin off a simulation to practice beforehand or something like that. I think one of the big benefits here is the fact that with this you have the compute where if you use something like Kubernetes or a similar kind of a task queue system, you have the ability to kind of just throw jobs at the wall and just have it being handled transparently without having to think about the architecture that much. Well, I mean, you have to set up the Kubernetes cluster or whatever, but it's an architectural decision that kind of gets moved away from your immediate responsibility, and that I think is a nice quality.
I think we're 10 minutes over, so yeah, should probably wrap. Thanks a lot for sharing your Turing Pi
Join.
sites and stuff. Very helpful. I was thinking of buying it, and I think you it dampened my enthusiasm a little bit. It looks like it's more trouble than it can be used for, but yeah, I'll still put it on my list of potential fun experimental learning things.
But part of the, I mean, if you use a CM Force, especially CM Force, it should be less trouble because then it's, as Liam mentioned, you have the whole support from Raspberry basically. Okay, it's we chose the Turing Pi RK1 because they were NPUs, and as Liam mentioned, we were thinking about doing machine learning on it as well. Okay. But with the CM4, there are many advantages. And
and you can use an NVMe slot for the RPi AI module instead, and get some NPU that way. All right.
Thank you, Liam.
Yeah, pleasure.
Okay. Bye.
Cheers.